Welcome back, everyone. Today, we're diving into a genuinely fascinating explainer on a problem that is absolutely pushing the boundaries of AI right now. We're going to demystify how artificial intelligence actually reads words that, well, aren't even there. Yeah, you heard that right. We are looking at the science of invisible words. This all comes straight from an incredibly compelling paper by Milan Straka over at Charles University. It's called CorPipe at CRAC 2026, Empty Nodes and Cross-Lingual Transfer in Multilingual Coreference Resolution. Okay, let's dive into this. Here's our roadmap for the complex NLP concepts we're covering today. We'll start with the invisible word problem, enter our hero CorPipe 26, break down its two-step architecture, see how it absolutely crushed the competition, and wrap up with its open-source future. All right, let's kick things off with Section 1, the invisible word problem, teaching machines to read between the lines. So let's introduce the linguistic mysteries sitting right at the heart of this research. I want you to imagine an AI as a detective. It's trying to solve a mystery, right? But half the clues have been completely erased from the crime scene. Now, human beings, we do this effortlessly. When we talk to each other, we leave out words all the time simply because the context makes our meaning super obvious. But for a machine, a missing subject in a sentence is a massive blind spot. So how exactly does an AI read words that aren't actually there? To really understand this hurdle, check out this Czech phrase, řekl, že nepřijde. Now, look at the English translation. He said that he won't come. Notice those words in parentheses? In what linguists call pro-drop languages, think Slavic or Romance languages, pronouns are frequently just totally omitted. Why? Because human speakers can infer who is doing the action based simply on the verb morphology, or just the context of the conversation. We naturally fill in the blanks. But for an AI, those missing pronouns are a huge roadblock. It literally just sees the verbs and has zero entity to attach them to. And that brings us to a foundational concept in natural language processing. It's called coreference resolution. Basically, this is the task of identifying and grouping together expressions that refer to the exact same real-world entity within a text. It's kind of like drawing invisible strings connecting words all across a document. For example, if I say, the president gave a speech, she was very articulate, coreference resolution is the AI drawing a string between the president and she. Simple enough, right? Well, how do you draw a string to a word that doesn't even exist on the page? Enter empty nodes. These are the omitted words that do not appear in the surface text, but they are absolutely necessary for accurate core reference modeling. And finding these empty nodes, that is the primary requirement for the CRAC 2026 shared task. It's an international competition designed to push multilingual core reference research forward. Because think about it, if you can't find the empty nodes, your invisible strings have absolutely nothing to tie onto. Moving on to Section 2. Enter CorPipe 26, the David versus Goliath of AI. To solve this exact problem, let's meet our specialized hero for today, CorPipe 26. This was the winning submission to the incredibly complex CRAC 2026 shared task. It was built by Milan Straka at the Institute of Formal and Applied Linguistics at Charles University in Prague. And this system didn't just solve the problem for a single language. No way. It tackled an astonishing 27 datasets across 19 different languages. It even handled 2 brand new additions to the task, Dutch and Latin. Now, what makes this whole explainer so compelling is the context of the competition itself. The 5th edition of this shared task had a very explicit focus. They wanted to compare highly specialized pipeline systems like CorPipe 26 against massive general-purpose generative large language models, or LLMs. So we are essentially looking at a real David versus Goliath scenario here. On one side, you've got these massive models with billions upon billions of parameters trained on the entire internet. And on the other, a strictly multilingual, highly optimized, specialized system that's trained simultaneously on all provided datasets without even being told which language it's looking at. Now, what's really interesting about this slide is how we transition into Section 3, the two-step architecture, engineering the solution. Let's look under the hood. You see, instead of trying to do everything all at once, CorPipe 26 strategically breaks this massive cognitive problem down into 2 distinct sequential tasks. Step 1 is simply to predict those invisible empty nodes. Then, once those hidden subjects and pronouns are brought into the light, Step 2 performs mention detection and coreference linking. That's when it draws those invisible strings between the newly visible entities. So for step 1's architecture, the text is passed through a pre-trained multilingual encoder called XLM Roberta Large. But here is the absolute genius part. For every single word in the input text, the system generates up to 2 empty node candidates. Then it uses 8 specialized heads to process these candidates. Basically, one head predicts if the candidate is actually an empty node. Other heads predict things like the form, the lemma, and the part of speech. And finally, the 8th head uses self-attention to figure out exactly where in the word order this invisible word needs to be inserted. It is literally meticulously reconstructing the missing pieces of the puzzle. Then, moving right along to step 2, mention detection and co-reference linking. With the empty nodes now predicted and placed directly into the text, CorPipe reads the document one sentence at a time. But it intelligently expands the context by including up to 50 following tokens plus the previous context. The identified mentions, which are represented by their first and last tokens, are then evaluated. Through a super sophisticated self-attention layer, the system figures out the most likely antecedent for each mention. It even allows a mention to point back to itself. That's how it indicates the very first time an entity is introduced. So clever, right? Which brings us to section 4, crushing the competition, the quantitative impact. Okay, so all this brilliant engineering is great in theory, right? But how did it actually perform out in the wild? Well, CorPipe 26 didn't just hold its own against the massive generative LLMs, it beat every single one of them. Yeah, in the dedicated LLM track, our specialized hero outperformed all other submissions by a solid 2.8 percentage points. You really have to keep in mind, these generative models require vast amounts of compute power, and yet this specialized pipeline outperformed them in strict quantitative metrics. And honestly, if you look at the unconstrained track, the victory is even more dramatic. CorPipe 26 achieved a massive 9.5 percentage point lead over all the other submissions. I mean, we're not just talking about a minor incremental improvement here. This is a complete domination of the shared task. And this brilliantly illustrates exactly what we're talking about. The official CRAC 2026 shared task results on the mini test set really show this domination. The CorPipe ensemble, which, by the way, is an ensemble of their 7 best models, hit a head-match score of 77.11%. Compare that to the top LLM submission, LLM Lattice NLP, which is sitting at 74.32%, and the baseline model, which is way down at 54.54%. By breaking the problem down and utilizing highly specialized architectural choices, CorPipe literally left the brute force approaches in the dust. Finally, Section 5, an open source future. What's next? Now, what I really love about this paper isn't just the victory lap. It's the real-world value they provided to the community. There's actually a surprising and completely fascinating fact buried in the paper. The researchers were working on this sort of unfinished masterpiece, a one-stage variant of CorPipe 26 that predicts empty nodes, mentions, and coreference links all at once in just a single pass. Now, while they didn't quite finish training it in time for the official submission deadline, their internal tests showed something crazy. The single-stage model actually slightly surpassed their winning 2-stage model on the development set. This points to an absolutely incredibly exciting future direction for this technology. It's going to make things faster and even more unified. And honestly, the best part? You can use this right now. The researchers evaluated the impact of varying model sizes going from the 269 million parameter OMD5 base all the way up to the 5.4 billion parameter OMD5 XXL. And they haven't kept this breakthrough locked away in a vault. The source code, along with several pre-trained multilingual models, are available right now under open-source licenses on GitHub and Hugging Face. So whether you're an academic or working engineer, you can go download these tools and start running multilingual Coreference resolution with MD node prediction today. Which really leaves us with a truly profound question. We've seen today that, with the right architecture, an AI can be taught to act like a detective. It can infer the missing pronouns and invisible strings of our languages, matching and even beating massive language models in the process. So I'll leave you with this. If AI can now successfully read the words we deliberately leave out, what other invisible human nuances will machines learn to decode next? Thank you so much for joining me on this explainer. Keep learning, and I will catch you on the next one.